All right, we're back here, guys. We're working on chi-squared test. The first one we worked on was goodness of fit, chi-squared goodness of fit test. This one is the chi-squared test for independence, or sometimes we call it the test for association. Basically, we'll be looking for the question we ask, is there an association between the two, or are these two things independent? We're going to look at I dominance and minimum wage as examples. All right, so the way this test works is we have a single random sample. So one sample of individuals is chosen from a single population, one population, and then classified on two or more categorical variables. So they're asked, say, 2 questions or 3 questions or 4 questions or whatever. We want to check the relationship between the 2 variables. All right, so do you believe in climate change, and what's your political party? All right. Are you passing math? Are you passing English? So we're just asking these people 2 separate questions, and we're seeing, is there an association between the answers? All right, so for our hypotheses, so really our state is just our hypotheses and your alpha value. The hypotheses, the null hypothesis, is that there is no association between the 2 variables. All right, so like one does not affect the other. The alternative hypothesis is that there is an association between the 2 variables. All right, and this is where we would put context in right here. All right, and the way we remember this is ho, no. They rhyme. Ho, no. All right, no association. Ha, and. They both have the A there. All right, so the A and the O. Ho is no association. Ha is an association. All right, this is a chi-squared test for independence is the name of this, or you could say chi-squared test for association. Either one of those is perfectly fine. The conditions are we need one random sample, one sample for this guy. Later on, we'll do one with 2 samples, which is a different chi-squared test. Our large counts is going to be just like before. All of our expected values need to be greater than or equal to 5. But now we have a way to calculate them, and actually our calculator will automatically do it for us, but a lot of times we don't actually have to do the whole test. We just have to check these. So it's the row total, like the total of the row on the two-way table, the column total, multiply those together, and then divide by the table total. Like the bottom corner is the table total, like down here, like the big number, table total. The row total would be like there. The column total would be down there. All right. We'll do an example, don't worry. Independence, we need n to be less than 10% still. That's always a thing. All right, so we do the chi-squared test for independence. It's just called chi-squared test on your calculator. We're going to write down chi-squared out of that. We're going to write down our degrees of freedom, and we're going to write down our p-value. All right, we could calculate the chi-squared by hand, doing the observed minus the expected squared over the expected for each part of the table. That's not a total part of the table, by the way. To get the degrees of freedom, so this is a little different. The degrees of freedom is the rows, number of rows there are, minus 1, times the number of columns there are, minus 1. And this is not counting the total rows and total columns, because usually at the end of each one we have like a total. And then like down here we'll have like a total. All right, we don't count those. We count everything else in between. All right, so if we had, say, this, it'd be 1, 2, 3, 4. So it'd be 2 minus 1 and 2 minus 1. And it would just give us 1 degree of freedom. All right, there is a way we can actually, there's a way we can know that without actually having to do this calculation. So assume we know this number here, this number here, this number here, and all the numbers on the outside, basically. And the question then is, how many numbers do we need in here in order to know all the other numbers? That's actually what your degrees of freedom is. So if we know one of these numbers, so like if I just know this one right here, I can subtract to get this one, I can subtract to get this one, and then I can subtract to get that one. That's why my degrees of freedom is just 1, because if I know 1, I know all the rest. All right, that's how degrees of freedom work. Now you finally know. All right, and then we conclude. If P is low, reject the ho, then write a sentence in context about the alternative, whether or not there is an association. All right, so this is a fun one. We usually do this in class. If you want to do this at home, you can pause the video and check this out. Figure out which eye is your dominant eye. The way you find out is you make a little cross with your hands when you have this little circle or little triangle or whatever that you can see through. And make sure there's something now that you're looking at that you can see in between your hands. Like I can do it across the room with my TV or a light switch or something. And then one eye at a time, close your eye. For one of your eyes, you should be able to see the thing in between your hands, and for the other one, you can't. For the eye where you can still see the thing, that is your dominant hand, or your dominant eye. I guess I should say eye. All right, so it's either your right eye or your left eye. So I've done this for a couple times, and this is my 3 classes last year came up with this data. So we also looked at gender here. So we had one sample, so one combined sample. All right, and we had right eye dominant females, left eye dominant females, right eye dominant males, and left eye dominant males. Looks like people were more right eye than left eye here. All right, so is there a relationship, down here, is there a relationship between gender and eye dominance? All right, so we're looking for a relationship between the two. This is what tells us we're doing a chi-squared test for independence. Are these two things, gender and eye dominance, independent or not? Or does having one gender cause you to be more likely right eye or left eye? All right, so we're going to do our test. So let's see. Our null hypothesis is no. So there is no association between, and our two variables are gender and eye dominance. And eye dominance. All right, and means there's an association. So there is an association between gender and eye dominance. All right, they didn't give us anything for alpha, so we'll go with 0.05. All right, we're doing a chi-squared test for independence, or we can call it a test for association. Either one's fine. All right, I'm telling you that this was a random sample. We'll go ahead and just say it's a random sample. We'll pretend. All right, our expected counts, we don't know them, but we need them to be all greater than 5. All right, we're going to come back to that. And for independence, our sample size is 89. It's definitely less than 10% of all, and I guess I took my sample out of students, so this would be out of all students. All right, we're going to come back to this expected count, so don't forget about it. We're going to come back to it. All right, we could calculate it. The way we would calculate it is we would do for this one here. We would do 67 times 49 divided by 89. So this would be 67 times 49 divided by 89. This one here would be 22 times 40 divided by 89. It's the column total, row total, divided by the table total. And that's how we do it. All right, but the calculator is going to automatically do it for us, so we'll just wait. All right, we're doing the chi-squared test on our calculator because it's not the goodness of fit one, so it's the chi-squared test. In order to do that, we've got to put the numbers into our calculator. But it's not one list, and we don't want to do this as 2 separate lists. We want to put them all together in the calculator. And the way we do that is we put them into a matrix. So if you see the word matrix right here in blue, it's right above x to the negative 1. We press second, and then we press that button. We go over to edit. We just choose the first one, A, and we're going to put the numbers in. All right, so we need to say that it's 2 by 2. So you're probably going to have to type 2, press enter, type 2, press enter, and then you should have blank here, and you're going to type in 38, 11, 29, and 11. You can just press enter after each number. And there we go. There's all the numbers typed in. So now I'm going to quit. Notice I didn't type anything into B. Didn't even touch B. So now to do the test, I'm going to go to Stat, Test, and I'm going to go to chi-squared, which is just option C. All right, my observed, these are my observed values, so I put them in A. Expected, they're going to automatically put them in B for me. The calculator is going to calculate them and going to put them in B. And I'm just going to press calculate here. And there's my chi-squared value, 0.303, and my p-value is 0.58, and my degrees of freedom is 1, because if we know one of these numbers, all the other ones we can calculate. So it's pretty low chi-squared value. 0.301, I guess it was. Our p-value was pretty high, and our degrees of freedom was 1, 0.58. And this was calculated by 2 minus 1 times 2 minus 1. All right, now we're going to go back to those expected counts. We need to, don't forget those. So if we could go back to matrices, second matrix, and we go to edit, and we look at matrix B, there's our expected counts. It calculated them for us. So I'm just going to do this. I'm going to make a little matrix right under here, and I'm going to write in the expected counts. So we got 36.9, I guess that would round to 36.9, 12.1, 30.1, and 9.9, I guess that would round to. And all of those are greater than or equal to 5. So now it checks out. So don't forget to go back and do this afterwards. Matrix B. Go back and do that. Put in the expected counts. All right. So now let's see. Our p-value is 0.58. Our alpha is 0.50. So since one day we'll reject something, I think. Since the p-value equals 0.58, which is definitely greater than 0.05, which is our alpha, we fail to reject. So there is no evidence for an association. All right, so we have evidence for no association. So there is no evidence of an association between I dominance and gender. All right, so there's our alternative hypothesis right there. We don't have any evidence for it because our P was pretty big. Or we could say no significant. I probably should say significant evidence. All right. So there's the walking through the steps on the calculator. Did I get the same numbers? 0.58 through 0.301. Yep, I did get the same numbers. I guess that would round to 0.302. Not a big deal. There it is in case you want to see it again. And another example here. I'll try and go fast here. So in a recent Pew Research poll, responders were asked if they support raising national minimum wage to $15 per hour, and they were asked which political party they identify with, Republican, Democrat, or Independent. The results are summarized in the table. So I looked this up this morning and got these numbers basically from a poll result this morning. So these are not made up numbers. Is there significant evidence for an association between political party and people's stance on minimum wage? All right, well, we are doing a chi-squared test for association. All right, that's what tells us we're doing that because we have all this table values. And here is our data right there. All right, the table totals we're not going to need. We just need those numbers right there. So our null hypothesis is, oh no, there is no association between political party and minimum wage. And our ha would then be an association. So there is an association between party and minimum wage. All right, and they didn't give us an alpha, so we're going to go with 0.05. It's a chi-squared test. You can say for association or independence. Either one is fine. I'm going to say association this time. Don't write chi-squared test for ass. Write out association. Lazy. I know some of you. All right, so let's see. I'm assuming they interviewed a random sample because it's a Pew Research Center, so it probably should have said that, but I didn't write it this morning. My bad. So we probably have a random sample here. So let's see, our expected counts, we don't know them yet, but we're going to come back to them. We need them to be greater than or equal to 5. And independence, our n equals 1,000, right? Here's our n, which is definitely less than 10% of, I'm assuming we're interviewing people in America, of all Americans. All right, we'll come back to the expected counts, don't forget. We're going to do the chi-squared test on our calculator, but first we need to put these numbers in. All right, so let's see, on, and let's get out of this. So let's see, second matrix, edit, and we'll just go with A. And let's see, one of them's 3, one of them's 2. I don't remember which one's which, so let's try 3. Yep, that makes us go down, cool. So 3 by 2, and then we'll put in the numbers. So we got 142, enter, 188, doesn't like you want to hit numbers twice, there we go, enter, 300, enter, 50, enter, 214, enter, and 106, enter. So there's all of these numbers right here into the calculator. There we go. We're going to quit that. We're going to go to stat. We're going to go over to test, and we're going to go down to letter C. There's our chi-squared test. And we put our observed in A. Our expected will show up in B, and we can calculate. Oh boy, that is a big chi-squared. 137. Whew. And our p-value is e to the negative 30. Whew. So our chi-squared value is 137. Our p-value is essentially 0. And our degrees of freedom, though, let's see, we had 2 by 3 on the table. So it was 2 minus 1 times 3 minus 1. So that's 1 times 2 is 2. And let's see, did our calculator calculate that? It did. Yep. And this was 1.4 here. Times 10 to the negative 30th. That means there'd be 29 zeros in front of that. Our p is essentially 0. All right. It's the smallest p-value I think we've ever gotten. All right. So now we say since the p-value equals 1.4, I'm not even going to try and write out the 30 zeros, times 10 to the negative 30th is less than 0.05, our alpha, we are going to reject. Our p is low, so we reject our HO. That means we have significant evidence, very significant evidence. We have significant evidence that there is an association between political party and beliefs on minimum wage. And then if you want to, we can go back up and look at the chart to see. Looks like Democrats are almost all for increased minimum wage. Republicans, it looks like there's more of them for not raising minimum wage. And independents, it looks like there's more of them for minimum wage as well. So it looks like Republicans are kind of against it. Democrats are for it. Independents are also for it. And in total, about 66% of people are for minimum wage. Now, we forgot something. We never went back and did our expected counts. So we would have been marked wrong on the AP exam if we didn't catch that. So now we want to go back in, second matrix, and we want to check out B. Oh, forgot we need to go to edit B. If we just go to B, we could press enter and it can display it on the screen. There's our expected counts. So we need to write those down. We can just put them right here. So 216, 229, 209. I'm not rounding, but yeah, they should probably be rounded up. That's okay. 113, 120, and 110. And those are definitely all greater than or equal to 5. And if we got to label this expected. And there we go. Now we've got full credit because we went back and we did our expected counts. So don't forget to go back and do the expected counts like I just did there. All right, so that's this one. Again, sorry for the link, but these tests take a long time to get through.